Very happy to talk about the wind power that in this lunch talks. But first of all, I'll give a quick outline about what I plan to talk today. Because I'm not sure if everybody's familiar with wind power, so I will briefly talk about some basic idea about how we use the wind power. Then I will talk about what is the potential of the wind power in the net zero energy system. Then I'll move to a little bit more technical detail about the characteristic of the wind energy and how it link with the energy demand we have in our world. And at the end, I'll talk about different technology. How can we integrate the wind power to the energy system through different energy carriers? So first of all, a very quick introduction about myself. So I just joined Empa in the Urban Energy System Lab last summer, and I mainly focus on energy system modeling. But before I joined Empa, I have a PhD at the University of Birmingham in the UK, and my research topic is about integrate wind energy with the energy storage in general. So that's why I'm here, I guess. And after I finished my PhD, I moved to another university in the UK at Cornwall, very southwest of England, focused on understanding the floating offshore wind and how to integrate with energy system. And so that is a little bit about my background. So I do a lot of research related to the wind power and also the energy system. So first of all, I would like to quickly introduce what is the basic element about the wind energy or wind power. So if you want to understand how to extract the wind power, so that is a very basic equation. You can see it's linked to like 4 key parameters. But basically, the density of the fluid that moving is one of the key important things, and how is the struck area of this kind of wind turbines and another key factor. And the last factor you can see here is the wind speed, is how fast the wind blow, and you can see there's a factor of 3. So if we have a double the wind speed, the wind power can be like 8 times bigger. So that is some basic element I would like to introduce. Another element is like there's one very important factor we call this power coefficients. That is how much like power you can extract from wind power into the turbines. So based on those things, people can use this power coefficient uh, property to draw a diagram on different kind of turbine, because I guess you probably know the typical turbine is the one you can see right now. We call this the horizontal turbines. Give me a second. Now, I usually have 3 blades, but however, that's not the only kind of wind turbine. So there's a different vertical wind turbine could have different design. And you can see there's this one's more like cylinder. Second one is like a multiple blades, and this one is like even have kind of no blade, but it's the vertical devices. So low thing is all kind of a wind turbine can convert wind power to energy. Yeah. But however, the most typical one you'll see is like the vertical one, very big, tall, and usually have 3 blades, but sometimes could be 2 blades. And that is by far the most kind of efficient wind turbine. You can extract more wind power, which means the power coefficient is more close to this ideal power curve, ideal like a power coefficient curve. So that is roughly about the wind turbine. So I have to say, because you can see the wind power is proportional to the struck area, which means if you have a double the length of the blades, you have 4 times bigger of the power. So that's why it's important that people try to get bigger and bigger turbines. But however, and based on this diagram, you can see there are also still some small size of wind turbines that can be used. Yeah. Sorry about if there's a noise in the background. And okay, so that's roughly about different kind of wind turbine. So So now I would like to introduce quickly about the trend of the wind industry today we have. So first thing is you can see, you probably will know is if on the ground there's more like turbines, we'll cause some like a turbines to slow down the wind speeds. So when you go to a place have no like building or construction or object on the floor, the wind speed will be lower at the lower height. And that's why most of the onshore wind turbines are installed like at open area, and even there's a lot of offshore wind turbines installed in the world right now, is because there's not much like object on the sea, so it can slow down the wind speed. So that's why you can see like today, typically the turbine we have on land could be like 2 megawatt, but you can see in the future there's a trend to go bigger and bigger. And this trend is even go more like a bigger difference for the offshore wind turbine. And so today the offshore wind turbine could be like 8 or 9 megawatt per turbine already. It could be over like 150-meter the height. And there are some people building like 15 megawatt already. So the main reason why the turbine offshore is much bigger than onshore wind turbine is how we do the installation for the wind turbines. So for the onshore wind turbine, you need to transport the blade from the manufacturer to the place you want to install wind turbine. And sometimes this could be very difficult because the blade needs to have a very strong structure. So usually you will be manufactured in one single pieces. And if it's, you can imagine if it's more than 100 meters long, then it'll be very difficult to transport from one place to another. So that is one of the key factors to could limit it people install big wind turbine at a place they want. But however, if you're talking about offshore wind power or offshore wind turbine, because there's will be less like limits about how you transport the thing on the sea, so there's a better chance to build a bigger turbines. So now I just have a quick introduce how the wind turbine looks like. So now I would like to be a little bit more focused on how this wind power is linked to the energy demand. And at the end, I would like to introduce why it matters for the people we have in Switzerland. Yeah. So first, this is a typical an example diagram I have for the wind power in the UK in 2018. So you can see there's two curves. The blue one is the curve in winter, and the orange one is the curve in the summer. So you probably can see, even UK considered as a windy places in winter, you still could have a couple of days, like 3 or 5 days, continue 3 or 5 days have kind of comparatively low wind generation, and the next 2 or 3 days you can have a pretty high like a wind generation. So that is the typical pattern you might see from wind power. And if you look at the orange line, you probably can see that the wind generation is usually lower in summer. So if we convert this diagram into a step back to look at this profile in the longer period of time, and you can see on the right-hand side is a 36 years wind power statistic numbers. So basically, this diagram tells us the average, well, the distribution of power capacity factor in each month in the years. So obviously, you probably can see for sure in winter, the average power capacity is much higher than the summer, and the summer could be lower to like only 25%. And by in winter, it could be higher like to 40 or 50%. But let's say another message is important to see here is, okay, even in winter, it's very windy, but sometimes in certain year, it could be very windy up to like 65% of the capacity factor, or it dropped to even 25%. So in this case, you can see like if in the future, a lot of wind power will be the main source in the energy system. So you could have some of the months in the year that have a very low generation in the winter, in the specific months. So this will come to like hopefully they can give you some idea about the fluctuation of the wind power. So usually we break down into different time scales. So in within like a couple of hours or even just a minute, you can have a strong gust or caused by the turbulence of the wind power. But also you can have some variation in one day due to the temperature change in the day and night. And in a few days, you can see that could be some like weather front or some storm coming. So you can have a continued couple of days have a high or low wind generation. And at the end, you for sure you have a seasonal variation and the yearly variation we have mentioned earlier. And in the even longer term, like the climate change could also impact the power generation in certain regions as well. So those are the factors that affect the intermittency of the wind power. So once we see this the wind characteristic, I want to give an overview about how is the potential of the wind power in the Europe. So I just I got some result from the report in 2020 about what could be the different net zero scenario in EU energy system by 2050. So you can see that lows at the top is the electricity generation in EU, and at the bottom is kind of the um, the energy mix of the electricity generation in the system at that time. And one of the thing I want to point out is you can see the wind power is this a little bit like blue color. So you can see in many scenarios, wind power could account like more than 50% or even up to 70% of the whole electricity generation. So that means that will, if you link to the previous intermittency of the wind power, you can imagine in the future, wind power could cause some problem in the energy system. So how can we analyze the impact of wind intermittency to the energy system? So usually we will use we can start to use a simple way called residual load analysis. So this is a typical diagram about how we do the residual load analysis. So first, on the left-hand side, it is just the load duration curve. So basically, you just get the electricity demand or electricity load curve in a year, and you sort it from the highest value to the lowest value. And you can see in 1 year you'll get the one very peak load. And in Europe, probably is happening in the cold winter days that you have high demand. And if you sorted this number, the lowest point usually could be like in a warm summer day, well, maybe not warm, on the day that don't have too much heating or cooling demand, and probably the holidays, so the demand will be low. But usually, this curve can help us to understand first what could be the peak load, and second what could be the like a minimum load or the base load of this duration curve. So once we analyze this duration curve, we can convert it another curve. We call this residual loads. But basically, residual load is the electricity demand you see early on left-hand side diagram and subtract the renewable energy generation. So here could be like wind or solar. So what could happen is if you have an original electricity load here, then you can extract the renewable generation, then you'll get another curve. So what this curve can tell us is if the peak residual load means, okay, the time that you still need to have the electricity generation from the sources, not from renewable energy, then probably could be battery, the other fossil fuel power plant or pump hydro, whatever the other thing combined together. That is the peak demand you need to have to make the energy system run. And on the other hand, you can see sometimes the residual load could go negative. That means that renewable generation is higher than the demand you have. So sometimes we call this like curtailment. But if you have energy storage, then you can store it. But that is some basic thing we can do. And later, hopefully, I'll quickly introduce this. If we use this idea to apply some numbers, then we can see how the penetration of renewable energy, for example, wind power, can affect the whole energy system and could affect the residual load. So this is an example. I put it using the UK data, but hopefully for different region in Europe, you still have the same trend, means demand high in winter and a bit lower in summer or in the springtime. So this is the diagram. We have like 20% renewable energy share, and I make a certain assumption. For example, wind power is a bit higher. It's about it's 4 times higher than the solar generation. And you can see that the rest of the curve with the different color is the residual load. And those color means the blue one means is happening in winter, and red one means happening in summer. So you can see if we have a lot of renewable energy, then at winter time you still have like peak residual load you need to meet. So after we do this certain calculation, they can convert this diagram to different renewable energy share. Could be 20%, 40%, even 60% or 80%. And based on the diagram we have earlier, you can see in Europe, probably could go for like 50 to 75%. Then the result could be like between these two diagrams. And if you look carefully, when we go for like even over 40% of renewable energy, you start to have some curtailment. And if you go for 80% of renewable energy, you will see like nearly 40% of the time that's in the electricity system, your generation is just more than what you need in the demand. So based on this, like a very simple analysis, you can find a key problem is if we have increased the renewable energy share to the plan we have in different like net zero scenario, you'll see lots of energy will be in the curtailment time. But at the same time, the peak residual load is still very high because in certain day you don't have the sun and wind, and then you just have still have a high peak load to be deal with. So that is some idea about this residual load. So since we know, okay, if we have a lot of renewable energy, especially wind power, that could cause some problem to the energy system. So how can we address this issue? So that's why people came to like the idea that like, okay, for wind power, we don't need to just produce electricity. We probably need to produce into a different energy carrier. So this is now I would like to introduce, there are several selected potential low carbon energy carrier that can be used in the future energy system. So at least roughly 5 of them. The first one you probably know is the fossil fuel plus carbon capture and storage. That can help us to reduce the carbon emission. The second one is the most typical one is we have produce electricity. However, if you don't want to go for electricity, you can convert to hydrogen or even to ammonia or even to different synthetic fuel. And the reason we will choose those like ammonia and hydrogen thing is you just need some like basic feedstock like raw material to produce this energy carrier, for example, water or air for the ammonia. So based on this, you probably can see, okay, when we go from electricity to further down to synthetic fuel, there'll be more and more energy conversion. So the energy efficiency will be much lower and lower. So which means in terms of energy efficiency, we like to use electricity, but we don't want to go to further down. But however, if you consider different factors, for example, how easy to store the energy, in this case, electricity probably is not the best solution because it could be difficult to store in a large scale and long duration. So in that case, if you go further down from hydrogen to ammonia or even synthetic fuels, it will be even easier to be stored. But however, there are some other factors usually people consider is, for example, so how far you can transmit those energy. For example, for electricity, you probably need the electric cable, so that it's not very expensive and they have certain high loss. So that's why most of the international energy trading, they are mainly using like turn into fuel and transport in the long distance. And then another factor people also thinking about is how much infrastructure we can reuse. And in this case, ammonia could be an interesting case because um, they already have international ammonia transportation system in the world already. They have a lot of ammonia transport, like from maybe from Asia to the US or to Europe. So we have this infrastructure already today. So hopefully this can give you an overview about different energy carriers. But now I want to link, okay, how does it link to the wind power? So this is one of the topic that in my previous project we are focused on. So and because there's different way you can use integrate wind power to the energy system. For example, the the standard way will be like you convert wind power to electricity and connect to the electricity grid, but there will be another different pathway to use that. And by the way, this diagram was built on the offshore wind energy, but this can also apply for any kind of onshore wind power generation on the left-hand side as well. Okay. So the second pathway is if there's just too much electricity in the grid, you can convert to hydrogen and maybe connect to the gas network, then you can use it. But there's another pathway is, okay, at a wind farm, maybe we don't generate electricity at all. We just convert those wind power to hydrogen, then we can use a different way to transport those hydrogen. For example, there's a hydrogen pipeline. And for longer distance, you can even liquidize the hydrogen and transport by like ships for longer distance. And if you want to go even further, like a longer distance, so it's possible to use the to air to produce the nitrogen and use the hydrogen produced from electrolyzer to combine it to produce ammonia. Then because ammonia can store in the comparatively higher temperature compared to liquid hydrogen. So ammonia is easier to transport in a longer distance. So that is another possible pathway to use it. So the key message I have want to say here is, okay, if we convert wind power to those kind of synthetic fuel, it can reduce the intermittency impact from the wind power directly to the grid, but at the same time, it will increase the cost. So that is something usually we have to consider, like what is the best pathway or configuration we would like to use in the future energy system when we really want to integrate a lot of wind power. So that's why in the future, probably you will not just see the wind power produce electricity, but you can see wind power produce hydrogen and ammonia, and maybe you will be using when the wind and solar generation is low. And the last kind of slide I have, last two slide I have is, so why is linked to the Switzerland we have here? So you can see there's a news that last winter when the wind is really blowing strong in Europe, you can see that have a significant impact to the electricity price in everywhere in Europe. The prices drop in many countries, including in Switzerland. Basically, the spot market prices dropped to negative on the Christmas Eve day, I believe. So that is one of the examples to showing that, okay, even maybe in Switzerland, we don't have too much potential, but because since we connect to the European energy system grid, so if the Europe have a lot of wind power, it still have an impact to our energy system. So now I'd like to go to my the summary slide. So first, you can see wind power probably will be very one of the main energy source in the future, especially in Europe. And however, the intermittency could have a very significant impact on the energy system. And the second thing is there's a solutions convert wind power to the different synthetic fuel, could be hydrogen, ammonia, or methane. And this can enable long distance transportation or long duration storage. So this can help us to balance the temporal or spatial mismatch of the wind generation. And the last message I would say is that even Switzerland maybe have a low share of wind power in the future, but it still have certain impact to the Swiss energy system. So I would say it's quite important to consider that in our study. And I'll get to the last question I have in my mind. So in this case, since Switzerland will always integrate with the energy system in Europe, so can we provide I call this positive flexibility to the whole European energy system? And if we think about wind power, it'll be okay, in couple of days, you could have a strong wind or low wind period, and we could have a continued couple of days have a very low energy price and low carbon intensity electricity. So do we have the capability to store those energy? And in the longer term, in the seasonal variation, can we have store more wind power in autumn or even in winter to be used later? So that is something I think maybe we can think about it as a researcher in Switzerland. And that is all of my slides. Thank you.